same polarity as the corresponding return strokes. And again, the frequencies involved in such slow electric field changes would be down to just a few hertz. Next, I'm going to discuss return stroke electric field changes that are not resolved on this long millisecond scale. So what you see here, two columns. The left one is for electric field intensity on 170 microseconds time scale, and the right column is for magnetic flux density on 100 microsecond time scale. The distances are indicated 1, 2, and 5 kilometers. The next slide will show in a similar format electric and magnetic field waveforms at larger distances, up to 200 kilometers. Solid line is for first strokes, and broken line or dotted line is for subsequent strokes. Vertical scales are also indicated. At 2 and 5 kilometers, the initial field peak is readily discernible. It's primarily radiation. At later times, a few tens of microseconds later, we have this slow electrostatic ramp. Field is dominated by static field. 1 kilometer is almost entirely static, although there is a shoulder that is indicative of the initial field peak with significant radiation larger distances, electric field on the left, magnetic field on the right, 10 kilometers, 15, 50, and 200. And as distance increases, the initial radiation field peak is getting more and more pronounced, and the electrostatic ramp is getting smaller and smaller. 50 kilometers, 200 kilometers, there is no static ramp anymore. The field is dominated by its radiation component. The waveforms are bipolar. And such distances, magnetic field waveforms, they have the same shape, or essentially the same shape as electric field waveforms. This is an electric field waveform, vertical electric field waveform, shown on a longer time scale than on the previous slides. It is 700 microseconds across. So we see the initial cycle, zero crossing, opposite polarity overshoot, essentially the same on the previous graphs, on the previous slides. But here we can also see this second positive half cycle and second negative half cycle. So the overall waveform on this scale appears to be oscillatory. And there are two cycles within 500 microseconds. The corresponding frequency is somewhere between 4 and 5 kilohertz. And the initial cycle is the ground wave, the wave that propagates along ground surface. And this second positive half cycle is the ionospheric reflection, the first sky wave. The shape of this reflection appears to be different from ground wave. The reason is that observations were performed under daytime conditions when the ionosphere is lossy and acts as a low-pass filter. But it is indeed ionospheric reflection, as was shown by calculations even here. This is again vertical electric field waveform, model calculations, 600 microseconds across, and calculations were done for different distances, ranging from 100 kilometers to 400 kilometers, from black to red. And the initial half cycle waveforms were aligned, placed at the same time. And this second positive half cycle appears to be at different positions in time. And as distance increases, it moves closer and closer to the initial half cycle, indicating that this is indeed ionospheric reflection. And these calculations were performed by Steve Kammer of Duke University as part of our collaboration on this subject. And these calculations are for daytime conditions, similar to what we observed in experiment. Now, if we assume that this second positive half cycle is due to ionospheric reflection, then as a first approximation, you can assume that this zero crossing, second zero crossing, is the time of arrival of this first sky wave. And if so, we can find a difference in arrival time between ground wave and first sky wave, T1 plus T2, and use that information to compute effective ionospheric heights, reflected heights we did this for a number of first and subsequent strokes. Here's an equation, well known, to compute reflecting height using T1, which is difference in arrival times. And the distance R was obtained using NLDN data. This seems to be kind of trivial, except for one feature. We found that the reflecting heights, H1, are quite different for first and subsequent strokes in the same flashes. It's 81 kilometers for first stroke, 70 kilometers for subsequent strokes. And this is quite amazing because this indicates that the reflecting heights within the same flash are different by 9 kilometers or so. And the conclusion is shown here. It appears that the first stroke temporarily modified the ionosphere, the D region of the ionosphere, so that the electromagnetic signal of a subsequent stroke is reflected at a lower height. In other words, ionosphere descends in response to the first stroke, and this happens apparently by way of producing Ls that propagate radially across the bottom of the ionosphere to maybe 300 kilometers, and the effect remains for some seconds. So all subsequent strokes will experience lower reflecting heights. Anyway, these results are new, shown here in this workshop for the first time. Before, I was talking about either very close fields or quite distant fields. Now I'm going to show just two slides for very close and quite distant fields for the same lightning event. Two traces here, vertical electric field in each case, for the same nature lightning, 3 strokes, all labeled. The top panel is for a distance of 508 meters, and the bottom trace 46 kilometers. So this was recorded at Penn Landing, and this was recorded in Geyser, home of the University of Florida. Well, this V-shaped signature are evident here, and at larger distances is primarily radiation field component. We can see preliminary breakdown here, no seen at lower distances. Also some pulses apparently occurring in the cloud between strokes, not observed here, and very nice correspondence otherwise. The next slide will show the first stroke on an expanded time scale. Again, this is 508 meters, and this is 46 kilometers. Primarily electrostatic, primarily radiation, and we perform these measurements to examine in detail the slow front and fast transitions and return strokes, hopefully to gain some insights into the attachment process. And Hong Wong is performing some optical observations of the attachment process and so hopefully we can get some new insights using different observations. Moving along this electromagnetic spectrum to the right, now I'm going to talk about the very high frequency radiation, very high frequency radiation. These are the ranges from 3 to 40 megahertz, high frequency, 30 to 300 megahertz, very high frequency. The mechanism of radiation in these ranges is not well understood, but it is usually assumed, that radiation is produced by the electrical breakdown of virgin air. So there are many small sparks that occur during the formation of thermally ionized channels, and they are usually assumed to be sources of HF and VHF radiation. Here's an illustration of that. What you see here is an optical image obtained using an image converter camera of a positive spark in laboratory. It was a long spark, 5.5 meters long, and this is a high voltage electrode, positive, and this is a thermally ionized channel of a positive leader developing downward. And this is a fairly good conductor. Conductivity seems to be comparable to the conductivity of carbon. And also you can see this region that is called a spin zone. It's kind of conically shaped. And this region is kind of a transition between the thermal ionized channel, a fairly good conductor, and air below this extending